We're just going to keep doing some linear regression stuff. Just to mention, we've got that individual assignment, last one that's due today. We have the Excel assignment, which is due as late as next Monday. If you get that turned in early, I'll probably start grading them early so you can kind of start to get an idea about where your grade's at. Wednesday, I'll also bring in this thing and I'll post it on Canvas called Figure Out Your Grade Tool, because the weightings of the final or of your exams depend on how well you do. You can kind of play around with it and see, okay, if I do this well in the final, what might my final grade be? If I do really bad, what will my final grade be? And that way you guys don't have to email me asking me about, what if I get this in the final, what it is. So, and it's just kind of nice to actually, I feel like every professor should give one to you going into the final. That way, you know how to allocate your time, right? Like if I can get a 20 on this exam, but I still get an A in the class, I'm not going to waste my time studying for this. I can focus on the other classes. But hopefully me showing it to you and what we've talked about this semester, you could actually create them for yourself pretty quickly. So we've got that. I will likely start doing exam review on Friday. I'll put up an article after class today that I would like to go over on Wednesday with you guys. If you take a quick look at it, I appreciate it. Or if you just want to engage in the conversation when we're in class on Wednesday, you can do that as well. But we'll go over a couple papers. It'll have helped your understanding to have read them or at least glossed over the introduction to them before class. I don't expect you to read the whole paper and understand all of it, but look at the introduction, look at the conclusion, just get a general idea behind what the paper was trying to do. And it'll be like a little bit more of what actual economic research kind of looks like. And it doesn't have to be economic, it could be really any discipline, but what actual application of regression would look like. So that's kind of our roadmap. I put up a small set of lecture slides, and this is more so to have some things to remember what we were doing before. So I think we'll look here at these real quick. So we talked about these, all the intermediate steps. I'm not doing much with these, blah, blah, blah. Kept these in here because I'm double dipping using this for multiple classes. Here we go. So this is what I wanted to remind us of. So we had this idea of correlation versus causation. Right? So, right, it was this idea that if I just run a simple linear regression where I leave out an important variable x2, then when I look at the estimate, so what this is generally going to be, I'll write this on here. Usually when I write this, whatever slope coefficient I see for that x1 variable, it includes the true relationship. But when I leave out an important variable, call it x2, then the estimate I see from Excel is going to be a little bit biased, right? The estimate I see from Excel won't just be the true effect, it'll be the true effect plus this bias component. So what we can actually do ahead of time, and I'll prove this to you when we actually have some data, but usually we want to be able to say, well, I don't have this variable x2, which I know probably matters, right? It probably is related to my x1 variable, right? The covariance is probably something other than 0. And then B2 would be, this is the slope coefficient between our y variable and this x2 variable, if we could include it. Now, I'm going to show you an example where we do include it because we have the data and we're kind of building from a naive approach. But in practice, it's usually that I can't get data on x2, so I want to be able to sign this bias, right? Because whatever estimate I see is going to include this bias. So think about, for instance, maybe I'm interested in, whether or not, the years of education someone obtains has an impact on their income. Well, I run that regression, it picks up the true effect, but then maybe some other bias component from a variable that I left out, which is, I don't know, maybe just the natural intellectual ability of the individual, right? And so if I'm thinking about if I leave out this important, I might want to be able to put a sign on this. Because even though I find a positive amount, what if it's not the years of education that's coming from, it's the actual intellectual ability of the individual. And more intellectual individuals are likely to have higher years of education. And so I don't want to be kind of conflating that effect. So we can put a sign on this. Now, the variance of any variable is always going to be positive. And from there, we can probably use intuition, at least ahead of time, to think about what would the signs of these things be. So I'm going to show you an example in Excel in just a second, where we're going to look at I'm going to exhaust this COVID data until I got every little last thing out of it, right? But I'm going to do percent vaccinated, and then the variable I'm going to leave out, X2, kind of think about this, our X2 variable is income. Okay? And then the percent vaccinated is like our X1 variable. So if I don't include income in my regression, when I run this regression and get an estimate for B1, the relationship between number of new cases and percent vaccinated, what do you think the covariance is between the percent vaccinated and income? So as the income in a county goes up, what do you think is likely to occur with the percent of the population that gets vaccinated? It also goes up. This is true about like almost all, actually, I'll do this in red. This is true about like almost all vaccines, almost any healthcare, really. Higher income levels consume more of that. Right? This one's a little bit trickier, but if using intuition, if income goes up and I was able to include this in my regression, what do you think that coefficient would be between income and the number of new cases? It actually ends up being negative, right? And kind of the story behind this is, individuals with more income, right? They can take a little time off work, right? They don't go about their normal lives. Quarantine was not as bad for them, right? People with very low incomes, I got to keep hustling. I got to keep going to work. I got to pay my bills, right? And so higher income levels, we see activities that are less likely to cause spread. And so we expect fewer cases. Excuse me. Speaking of COVID, geez. So that is nasty. All right. So I've got that COVID regression file up there on Canvas. I'm going to open it up here because I know it exists. I think this is one I didn't save. All right. So this is a little bit different than the data we were using before. I merged some other stuff in. I think we can actually get a more accurate idea about what's going on with COVID. So I've got all these different variables. Here's my median household income. Here's my percent vaccinated. And here I did cases per person in the thousands. So this would be like 48 people out of 1,000 in that county got COVID. Even though you can see like the number of cases is 2,700. Well, I factored in the population and kind of made this a little bit more interpretable. Okay. So I'm going to run a really naive regression. So I'm going to go to my data analysis, regression, my Y variable. I'm going to select this cases per person. And then my X variable, I'm going to scroll up because it's starting new. I'm just going to look at the percent vaccinated, right? So I selected my labels. We'll call this naive regression, and we will zoom in so we can actually see it. Well, just with the percent vaccinated, I'm only explaining about 4% of the variation that exists in the number of new cases per person. But I can still come down here and look at this and say, okay, for every 1% more people get vaccinated, because that's the units of my X variable here. So don't get this just confused with like log stuff. The units of this X variable is the percent of the population vaccinated. Right? So if 1% more of the population is vaccinated, the cases per 1,000 people would fall by about 0.25 people. Right? So for every 4,000 people in the county, I'd have one fewer person kind of get COVID if I saw a 1% increase in the percent vaccinated. And I can say it's significant at what levels? All of them, right? Its p-value is 0. I can reject the null, which is that the relationship is 0 for every single level. So it's, I guess, okay, cool, the vaccine's working. But I then say, okay, well, look, I know that potentially there's a bias in that estimate, so that negative 0.25. That's what I observe in Excel, but I know it's going to be biased by this amount. Now I can put a sign on that bias, right? A negative times a positive divided by a positive. My bias should be negative here. So the estimate I see is going to be a little bit lower than what the actual value should be, right? So if I then include X2, which we said was income for us, into the example or into the regression, it should eliminate this bias component, and I'll only pick up that true effect. Okay. So I'll go here, I'll go back to sheet 1. I'll go to data analysis, regression. I've got my Y variable selected. Well, I'm going to have a couple issues here. So I'll show you both of them. So if I try to include income and the percent vaccinated, so I can select the income column and I can select unemployment. It looks like I should be able to run this regression, and it gets mad at me, right? I can't remember if I showed you guys this yet. If I did, what do I have to do here? What's the problem? Yeah, they need to be next to each other. For whatever reason, Excel can't do this. So I'm gonna just move things around a little bit. I'm gonna move this over. I just inserted a column, so I had some room to move things. And then I'm gonna move these back so everything's next to each other. Okay. Now, I forgot about an issue I think I have in this data set, and we're not gonna use it yet. This is a good time for me to kind of show this to you. So if I look at this unemployment variable, because this existed in the income variable as well, I just remembered to get that on. If I come down here to the very last thing, this shows me all the values I could see. Some of them are blank. So what I'm going to do is hit select all, click the blanks, hit OK. So on any of your individual assignments, some of you some problems with the logs. You can just, I think I told every single one of you just to get rid of the zero values just to make it easier. This is how you would do it, right? Use that filter tool. Here I didn't have zeros, I had blanks. Oh yeah, it's unemployment rates in Alaska in these counties where like nobody lives, right? So who cares? We can get rid of that. We'll be okay, I think. So we'll delete these rows. We'll make a note of it in the table that we show people, but we get rid of those. So now, if I want to use that unemployment rate variable, I can, and it won't give me any issues. Before, when there was blanks, it wasn't able to run the regression. Okay. So here, we should see a coefficient once I run this regression where I include percent vaccinated and household income. We said before that the estimate I see had this huge negative bias in it, right? So once I include income, this goes away. I should end up with a new estimate that's a little bit closer to zero, or it could be positive. It could flip the sign. I can't remember, but we'll see. So we'll hit OK. Sure enough, I'm looking at this when we zoom in. First of all, I've increased the R squared up to about 12%, right? So that's good. These are both highly significant, right? These p-values are basically zero. And now it looks like the percent vaccinated, not negative 0.25, but about half that size. So just including this one omitted variable, which is household income, biased our results by quite a bit, right? What was the bias component? Well, if the new estimate is negative 0.12, what did the bias have to be? I just eliminated that bias and it fell by, or it got closer to zero by about 0.13. So our bias component had a value of negative 0.13, right? Because now after we include that variable x2 in the regression, the estimate we see is negative 0.12. So once we included that in the regression, we eliminated that bias, or we eliminated, negative 0.13 from that equation. Any questions there? So where I was getting that 0.12 is from right here. Actually, this was close to 0.13. So if we went out to the third decimal, I guess I should have rounded this a little bit better. But that's where I was grabbing that from. Yeah. Median household income.
Yeah. And it has this coefficient.
Okay, so we can interpret that as well, right? So here, for every 1% more people vaccinated, the number of new cases per 1,000 fell by 0.12 people. And for every $1 increase in household income, the number of new cases we would predict in that county would go down by 0.0003 per 1,000 people. Well, that's really small, but why? It's the effect of a $1 higher median income. We probably want to know something like, well, if I was looking at a county and let's say they had a $5,000 higher average income, well, that's substantial. I'm comparing different counties now, right? So I had the effect of $1 I could just multiply it by 5,000. And a county that had a $5,000 higher average income, we would predict the number of new cases per 1,000 people for them would be 1.85, or almost 2 people fewer or lower. Yeah, so sometimes ahead of time, you can expect these coefficients to be really small. Because if the units is in dollars, the effect of $1 increase in like anything is going to be pretty, magnitude is going to be small. But if we know the effect of $1 and we've treated this as a linear relationship, I can find the effect of $100 pretty quick, or 1,000 or whatever I want. It's a good question though. Other questions on that? 14 in here. All right, so let's go to data analysis again, because I eliminated this bias, but truly there's more than just one omitted variable, right? So it's actually like, equals. There's going to be the covariance between x1 and x2 over the variance of x1 plus the covariance between x1 and x3 over the variance of x1 plus all these other variables, right, are all going to be kind of causing a bias component. So that's why when we start with these simple linear regressions, it's like, man, I couldn't even put a sign on what the bias is in terms of I could put a sign on every single bias. But if there's 50 variables I think matter, I'm going to have 50 different bias components if I leave those variables out of my regression. Now, we usually don't think maybe even that there's 50 that we really are leaving out that are important, but I was using that to be a little bit exaggeratory. So instead, let's just use everything we can. So here I'll use percent vaccinated, household income, the unemployment rate, whether or not it was in a metro county, and here is the region of the country. So what's going to happen if I go all the way over to the south? If these are the 5 different regions, if I try including all of them in the regression, Excel is going to automatically kick one out for me, but it screws up my p-values for one of the other variables. This happened because there was 5 regions, right? It kind of started out as here's the region that this state is in. It has to be in one of these 5. Why now these indicators? What's my base group? If I include all of them, what's my what's my control group? What am I comparing to? I have to leave one of those out. If these are the only 5 regions that these states are classified as, I have to leave one out. So I will do that, and I will just leave out the south because it's easiest, and I don't have to move everything around, right? So now those coefficients on my different regions can all be interpreted as this is the effect or the change in the predicted number of new cases if the state is in this region relative to the one I left out. So relative to the south. Notice this is kind of interesting. So I mean, this is, we can gain a lot from this, but if I have a state that's in the west, northeast, or midwest, relative to a state in the south, we would all expect lower kind of number of new cases in those areas. And maybe this has something to do with the laws there. But maybe it's like behavioral differences versus people where the weather's nicer, or weather's not as nice. Maybe yeah. And then the Pacific actually has higher number of predicted cases in the south, which is also like maybe there is something to do with temperature going on here. I'm not sure. But right, we had to leave out one of those. But once I include these additional controls, like even in the socioeconomic control of unemployment as well, now I end up getting a positive coefficient here. So this every additional 1% of the population in the county that's vaccinated, I expect the number of new cases per 1,000 people to go up by 0.04. And that's significant at the what levels? Yeah, 90-95% confidence levels, or the 10 and 5% significance levels. Right? Now, I also can throw onto the end of there, holding everything else constant, right? In terms of the interpretation of the coefficient, which means the thought experiment is 2 states in the same region, whatever region that is, both either in a metro or not in a metro county, same exact unemployment rate, same exact median household income, but one of them gets 1% more of their population vaccinated. We expect that that county actually sees an increase in the number of new cases. And we can say that statistically is different from 0 at the 10 and 5% significance level, or 90, 95% confidence level. So this is kind of interesting, but there's two things. First of all, we always have to remember these are just evidence of correlations. Now we've controlled for a lot more factors here, but it's still just evidence of a correlation. And we've already seen there was biases that existed in variables we weren't including. If there's any other variable that we didn't include that is correlated with the percent of people who get vaccinated and correlated with our Y variable, which is the number of new cases per person, then it's going to be causing a bias in our estimate. So there might be some other important variables out there that we haven't accounted for. Like I said, seems like maybe with the region thing, maybe there's something like going on with temperature because it changes people's behaviors. Maybe it's something like, I don't know. Maybe you could look at like political affiliation breakdowns by county. Maybe you could add in some more demographics in terms of like age and things like that. I don't know why. Well, men are dumb sometimes, so maybe the gender breakdown matters as well. Like maybe we're way less likely to go to the doctor. We know that from data. But I could start including all these things to make sure that I'm like eliminating as many of those biases as possible. So that could still be going on. So like we shouldn't look at this and freak out and say, well, county's getting people vaccinated, just giving people COVID. Well, we know intuitively that doesn't make any sense, right? Now, what I suspect, without really diving too deep into this, what's probably going on here is as the percent of a county, as the percent vaccinated in a county is getting larger, what do you think might happen to the behaviors of people? Right? I'm not worried. Right? I know for sure for me, as soon as I got the vaccine, I was like, yeah, let's go. Like that's the roaring 20s, right? Like, let's go out and party. I'm doing everything I can now. So maybe there's a little bit of that going on as well. And we're not going to be able to measure human behavior. I mean, maybe I thought about this. Maybe there's like some geospatial, like they can track your cell phone, right? So they like kind of know how people are moving. I've seen them do stuff like this with some Chinese data. And they track the movements and see like, well, how much movement was there in this area? Like, so maybe we could somehow get a measure of that, but it's going to be really hard to control for human behavior here. But, it does point in a direction, like if we could, and we can control for that, then we really could see like what this impact of vaccinating more people vaccinated would do. I'd also be remiss if I didn't mention, like, there are ways. So this is like introductory regression. The next level, any of you, I feel like I'm always hoping some of you are interested in statistics, because we have a couple other courses in the econ department, and you dive into issues of like, how do I pick up a causal relationship here? So there's things that you can do, like comparing two states before and after, and one of them has some policies that restrict people's behaviors because of COVID, and one that doesn't. You then look at the differences, look at the difference in those differences. There's all these strategies where we can get at a causal relationship, but we have to walk before we can run. This is where we got to start. Okay. So there is, you can actually use these coefficients and not just always have to say, well, we might have left out an important variable here, or we might have, not be able to measure this accurately. There are ways of getting around that. There are ways of getting a causal relationship. It's just kind of the next step. Okay. And, we're explaining about 30% of the variation here. So still 70% that we can't explain. So there probably are some important omitted variables that we didn't include, since that R squared is rough, relatively low. Okay. Any questions on that? All right, I wanted to show you one other thing here, I think, with this data. So if I ask you like what variables here are significant, and let's say I said at the 90% level. So which of them can you say have a significant relationship with that Y variable, the number of new cases per person, at the 90% level, or the 10% significance level? What would you do? You would go through and compare the p-value to my alpha of 0.1. Every p-value that's less than 0.1, remember, we always start out assuming that there's no relationship, right? Or that slope between the two variables is equal to 0. So if I can get a p-value that's less than alpha, I can reject that. So if I reject that there's no relationship, I'm really saying there is a significant relationship between these two based off my sample evidence. So I go through and looks like this one's, the intercept is significant, right? Anywhere where I see e to the negative, that's 0, right? So I can reject here. So significant, 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 not a significant relationship. Kind of interesting that being a metro county or not doesn't seem to impact these number of new cases. Significant, significant, at the 90% level, significant, we already talked about, not at the 99. Now, there isn't as much variation here because I have a really large data set, so the p-values are all pretty small. But one way I could make my rejection decisions pretty quickly is using something I've kind of already showed you. So let's actually up here put an alpha value of 0.1. What's something maybe I could use? Yep, just going to use an if statement and say, look, if the coefficient's p-value is less than alpha here, comma, put the word significant, like there's a significant relationship. If not, I can't spell, put not significant, right? So I'm just using an if statement there. Then when I copy this down, it'll keep telling me my rejection decision for the next coefficient based off its p-value. However, if I keep copying this down, what's going to be one problem? Yeah, right. My alpha, I need that cell reference to always stay the same. You can shout out, I don't care. He's just trying to be polite over here. So, so we hit enter and I can copy this down. And now, sure enough, I pick up that only that metro count, or the metro variable is the only one that was not significant. So it's kind of a nice, easy way. Also, I can't tell you how many times I see people make mistakes because they look at like e to the negative. Let me see if there's one here. Like they look at this and think, oh, that's greater than 0.1. Well, first of all, let's take a step back and remember p-values have to be between 0 and 1. So 4.1, we should know, well, something here, we have to do something with this, right? So always remember anytime you see that e to the negative, it's basically 0. I actually hate that about Excel. That's how it put out does the output. I mean, scientific notation's all right in some situations, but like here, it just kind of sometimes can trick you. But if you use that if statement, it reads this basically as a 0, and it'll make that rejection decision for you pretty accurately. Any other questions here? Okay, so I haven't done this, but I want to give you an example. So I don't know what this is going to look like, but I think this makes sense. In my head, this makes sense. So let's go back, be very, I think I'm going to run a naive regression to really make this point. Maybe we'll look at something else after the fact. So if I'm thinking about, we can use other control variables as well, I guess, but if I was thinking about, let's say I can control for other factors and eliminate the bias. If I'm thinking about the percent vaccinated and the effect on the number of new cases, my suspicion, and I could be wrong on this, but I'm going to explain it. And when it comes to questions that you might see in the practice exams or that you could see on the final, sometimes I might ask you a short answer or a phrase, something like this. And as long as you could give me the correct intuition for that short answer, I would count it as correct. So this final is going to be a little bit different, and then it's going to be a little bit more short answer heavy, right? Because a lot of this stuff is like interpret this, or so it's going to be a little bit more like a little bit different of a format. Okay. So I would imagine that there's probably some threshold, right? So initially, the number of new cases as I'm getting more people vaccinated, it's going down, but not a ton, right? And then there's probably some point where I almost hit like this, what they herd immunity, right? Where like if I can get above a certain percent, it just like starts dropping very, very quickly, right? Like really sharp. So I'm thinking there's probably a negative relationship between these two, right? I don't know for sure, but I'm thinking it probably that it's as I get more people vaccinated, the number of new cases is declining, right? But it's declining at an increasing rate. So here, if I'm thinking about, a relationship like this, and I'm thinking about adding in a quadratic term, I would probably suspect that maybe that effect is negative, right? So it's decreasing, but at an increasing rate. Right? So an increasing rate would mean that that square component would be positive. Okay? So if I look at this, I can actually run that regression, right? Oh, actually, I don't have it in there yet. So all I would do is create a new column where I square that percent vaccinated variable, double left click to get it for every single observation. Go back up to run my regression. Now I'm going to select my cases per person as my Y variable. Here, I'm going to just run the naive one at first and just include percent vaccinated and percent vaccinated squared, just so we don't kind of add in all these additional things to look at. In practice, we would want to control for those things as well, but just to make it a little more simple here. And then zoom in. And what we actually see here, so it looks like it's a positive on the first term and then a negative on the square term. So it's actually increasing the number of new cases, but at a decreasing rate. So maybe there's, sometimes it's hard to interpret these because we don't know exactly where we're at on, like where we're at in the curve. Like maybe we only see data from here to here. Maybe this curve is more like this, but we only see the data is over here, right? So if we don't see really high if there's no high vaccinated counties to make predictions for, then this curve is not going to make as much sense as if most of the data is over here, or vice versa, right? Depending on what the relationship is. But once we run that regression, we can actually determine what that quadratic is going to look like. And what's more important is we could think about things like the marginal effect. So what's the effect of one more unit, right, or one more percent vaccinated at varying levels? So we'll use these coefficients. They're both highly statistically significant. And I'm going to think about different values. So I could think about what's the marginal effect moving from 0% vaccinated to 1%. And then what's the effect if I see a 1% increase in vaccinations, but it was starting at 10, 20, 30, 40, 50, 60, 70, 80, 90, right? So you can kind of think about the marginal effect for these different levels. Now I could make this more granular. I could do this like make the starting point be like every single percentage, but here I just kind of chose the tens to kind of make a nice point. So we said the marginal effect was I took a derivative of this function in respect to that x variable. So it was always kind of like b1 plus 2 times b2 times whatever that x variable was. And that was my marginal effect. So here it's going to be that coefficient on the linear term plus 2 times that coefficient on the squared term times wherever my starting x value was. Okay, enter. I got the marginal effect if I started from that starting point of 0. So starting out at 0, if I get 1 more percent of my population vaccinated, I increase the number of cases I see by 0.7. So it's not that I'm increased, right? It's not causal, but it's probably that, well, if I was starting at 0, I still have like pretty much everyone unvaccinated. So 1% increase is probably not going to, it's probably correlated with all these other things that led to them having kind of higher cases to begin with. But I can kind of continue down here. I'll freeze those coefficients on those coefficients because freeze the cell references for those coefficients because I don't want those to change. But I want to copy this down so I can get the marginal effect from different starting points. Right? So notice, as I start to get up to these higher levels, well, now a 1% increase in vaccinations starts to decrease the number of new cases. So maybe the whole problem was I was treating a nonlinear relationship as linear, right? So when I was getting that positive effect before, maybe it's because I wasn't allowing it to kind of have this quadratic term, right? And so it looks like, if I was going to compare, first of all, that squared term is highly significant. If I look at my R squared relative to the naive one, so 0.08 compared to 0.04, just by making it a quadratic relationship, I explained twice as much of the variation that existed. So it's probably that model is, I shouldn't say probably, it is the case that that model is, more accurately fitting the data, right? So, where was I? Sheet 6. Yeah. So, maybe that's part of the effect as well, allowing for this quadratic term. So, if we really wanted to, we could run this again using the quadratic. We'll go data, analysis, regression. Now I'm just going to make sure I include all of this. Not the south, though. I have to leave out one category. Hit OK. Now when I look at the output, I've got a positive and a negative still, right? But this is probably going to be a very similar thing if I was to map out the marginal effects here. It's going to look like probably, when vaccination percentages are low, a 1% increase isn't going to do much. If anything, it's making people's behaviors maybe a little more reckless, but most of the county still isn't vaccinated. So it might lead to more cases. However, if I can get to these really high levels, well, then 1% increases in the percent of the population vaccinated. Now it's starting to decrease the number of new cases I see, right? So it makes a little bit more sense. And like I said, that positive and negative coefficient, very similar when we added in all those controls as well. A little bit different, but I mean, at least still significant and still the same sign. All right, it's a lot. Any questions over anything there? Want to hear something said again, or? So, yeah.
Can you just kind of go over again how you can filter and delete it?
Yeah. So if I go back to my original data, first of all, navigating this, Control Shift and just using my arrows to always go back up to the top, really helpful. So let's say I start out and this data isn't even filtered, right? So it just starts out normal. I go to that very first A1 cell, Control Shift over down, click that filter tool. Now it lets me sort everything. So the way that I generally do it, let me think. I don't think any of these other variables have anything weird, but maybe I don't want to include, let me say populations. Okay, this is a good one to do it. Maybe I'm thinking like, man, these populations are really low. I don't want any counties that have less than 400 people, right? Because that's just a really weird county, right, in terms of like how they're going to operate. And so I could look at, once I click on this arrow, it shows me every single value for this variable. Sometimes if it has too many, it won't show all of them to you, but for this one, it doesn't have too many. So I'm going to hit select all. And then I want to get rid of those observations that have populations that are lower than 400. So I select those two values, hit OK. Now I'm going to go over here and see how, like, if I put my cursor over the row heading, oops, if I select these two, right click and hit delete row, it just gets them, takes them right out of the data set. Although I don't want to delete those right now, but that's how I would do that, right? So that's how I would use the filter tool to kind of get rid of observations I don't want. And then if I hit select all again, it'll show everything to me here. Okay. I would suggest that if you're using your data for running regressions, you don't filter it like that. Or I mean, you filter it like that to get rid of the observations, but then make sure like everything is select all. So you're seeing the entire data set after you've gotten rid of those problematic observations. But yeah, that's the process or how you kind of get rid of some of those problematic observations. Now in practice, like with the log stuff, what would probably be better to do is you want to keep the raw data. So you would copy and paste the data set on a different worksheet and then delete the observations only off one. So you always have that original raw data, because maybe you run the log and then all of a sudden you're like, oh, wait, this actually is a lower R squared. It didn't fit as well. But now I deleted the observations, so I can't go back and run the, have the level with all the observations. So always try and practice. And if you did do that on the individual assignment, I'm not going to penalize you if you just deleted it or whatever on there. But in practice, we try to preserve that raw data if we can, because we never know kind of what our final optimal specification is going to be. Okay. Any questions on anything there? So we got a lot of good reviewing. So we did some quadratic stuff today, so talking about some marginal effects. We talked about if I've got multiple indicator variables, I have to leave one out if it's like representing a specific trait. We also kind of went through putting a sign on that bias. Right, that's something that I might expect you to know how to do. And just kind of some more experience, just hearing it more often, I think is helpful. Right? So if there's no questions, I think we'll probably get out a little bit early here today. Like I said, I'll put that paper up there. We'll kind of look over on class on Wednesday. Actually, I might put two of them up there, and we'll kind of discuss both of them. And then probably Friday, we'll already start doing some more exam review that looks a little, working through questions that look a little bit more like how the exam questions will look. So we'll do that Friday and then next Monday, and then we're an exam week. Okay. I think I mentioned at the end of the last class too, and if this gets too crazy, I might not be able to make this promise, but I think it shouldn't be an issue. I know our exam's Friday. If you want to take it earlier in the week, if there's a day that works for you, I can try to work out times if you want to take it early. Like I said, I'm pretty open. My schedule is pretty open during the week. So we probably can find a time. Otherwise, our exam is that Friday. Okay. Yeah. Yeah, so we'll meet and we'll just do review. If you don't want to show up, you don't have to show up. In fact, I was gonna do this today. Hopefully everyone has their eye clicker. If not, it's fine. We haven't been using it for a while. I just want to give everybody one more day to kind of get the 10 out of 10. Just answer with a letter. I'm doing it for all my classes, so it kind of depends on which class I start with first and how much time I have this afternoon. But I should be able to get it done today or tomorrow, where I will drop your lowest iClicker scores as stated in the syllabus, and then kind of put up a new category on Canvas that shows you what your grade is with your lowest drop, right? So you can start to get a more accurate idea about where your final grade is going to be. Okay. So any letter, whatever letter is your favorite today, I'll just give you everybody credit. So do that on your way out, and I'll see you guys on Wednesday.